Welcome to the Explainer. Today, we're diving headfirst into a classic dynamic programming challenge by decoding the longest common subsequence. If you've ever wondered how version control systems compare files or how bioinformatics algorithms align DNA strands, you are in exactly the right place. We're going to break down this intimidating algorithmic problem into really clear, bite-sized, visual pieces. Here is our game plan for today. 1. What is a subsequence? 2. The core intuition. 3. Building the DP table. 4. Populating the grid. And finally, 5. The ultimate optimization. Let's jump right in. Section 1. What is a subsequence? Let's set the stage. Before we even think about writing a single line of code, we really need to nail down what a subsequence actually is. The absolute key takeaway here is that it's all about preserving the relative order of the characters, not strict adjacency. You can skip over characters, you can delete them, but you absolutely cannot mix up the order they appeared in originally. This is fundamentally different from a substring, which requires all the letters to be right next to each other. Take a look at our two source strings here, a kabak and aebab. You can see how we're drawing connections between the matching characters. Now, the naive approach to finding the longest common subsequence would be to just generate every single possible combination for both strings and see what the longest match is. But honestly, that is horribly inefficient. The number of combinations just explodes exponentially. There's no way we're doing that. We desperately need a smarter path, and that's exactly where dynamic programming steps in to save the day. Moving to Section 2, the core intuition and our branching logic. For any character we evaluate from either string, we're basically forced to make a really simple decision. Do we include it in our longest common subsequence, or do we exclude it? To figure out our next moves, we start by looking right at the very first character of each string. We'll call this position LCS 00. This exact decision forces us down one of two distinct paths. Either we land in case 1, where the characters perfectly match, or case 2, where they differ. Let's unpack exactly what happens in each of these scenarios. Okay, case 1. If both characters match, like the A's shown here in the green box, we've literally struck gold. We confidently include them in our sequence. Because we found a match, we add 1 to our running length. And then, well, we just move on to check the remainder of both strings. Mathematically, our solution becomes 1 plus the longest common subsequence of whatever substrings are left over. But what if they don't match? Here we have an A and a K. This means we've hit a fork in the road. We can't possibly include both of these characters in our common subsequence at this specific position. Since we don't have a crystal ball to tell us which path ultimately gives us the longest sequence, we literally have to test both paths. First, we try excluding the A from the first string and compare the rest of that string with the second string. Then we try the exact opposite. We exclude the K from the second string and compare. It's kind of like exploring two alternate realities, and we simply keep whichever path gives us the maximum length. This reveals something absolutely beautiful. We are solving our massive problem by solving smaller subproblems that look exactly the same. This optimal substructure perfectly translates into a powerful recurrence relation. If the characters are equal, it's 1 plus the diagonal move forward. If they're different, it's the maximum of moving forward in string 1 or moving forward in string 2. This formula is the engine that fuels our entire dynamic programming approach. Section 3, building the DP table and laying the groundwork. Every dynamic programming solution needs a starting point, right? Or rather, an ending point. We have to establish our base cases. What exactly happens when we've completely run out of characters in one or both of our strings? The answer is naturally 0. If one string is empty, the longest common subsequence is just 0. So, we pad the last row and the last column of our grid with zeros. This gives us a super solid foundation to build from. With our strings along the axes, this nice, comfortable border of zeros is just waiting to be built upon. Which brings us to Section 4, populating the grid using the bottom-up approach. Here's the trick. We don't start at the top left. Instead, starting all the way down at the bottom right next to our zeros, we systematically work our way backward, cell by cell, row by row. For every cell, we just ask our formula. Do the characters at this row and column match? If yes, add 1 to the bottom right diagonal. If no, take the max of the cell below or the cell to the right. We iterate all the way until we reach the top left at index 00. And sitting right there in that top left cell will be our final maximum length.
Let's talk about the cost of this brilliance, though. Since we evaluate every single cell exactly once, our time complexity sits exactly at O of m times n, where m and n are the lengths of our strings. However, because we just built this entire 2D grid in memory, our space complexity also sits firmly at O of m times n. And for really massive strings, that is a ton of memory.
So let's fix that. Section 5, the ultimate optimization, slashing space complexity. Look really closely at the dependencies here. To calculate the value for any given cell, where does it actually pull data from? It only ever looks at the cell directly below it, the cell immediately to its right or diagonally down right. Notice anything? It never looks 2 rows down. It never looks way up at the top of the grid. This is a huge lightbulb moment. It illustrates that our full grid is essentially hoarding useless history. Once we finish calculating a row, the row below that becomes completely irrelevant. We actually only ever need to maintain 2 rows in memory at any given time, the current row we're populating and the previous row just below it that holds the data we need. By intelligently tracking just those 2 active rows and swapping them as we move up, our time complexity stays exactly the same. We still do O of m times n work. But our space complexity, we've successfully slashed it down to an incredibly efficient O of n. We went from needing a massive memory-hogging 2D grid to just 2 simple lightweight arrays. That is the power of noticing optimal substructure down to the memory level. We've taken a pretty daunting algorithmic concept, broken it down into a super simple binary choice of matching or not matching, built a grid from the bottom up, and then squeezed every ounce of space efficiency out of it. Now that you've mastered the 2D grid and this ingenious space optimization for the longest common subsequence, what other daunting algorithmic coding challenges are you ready to conquer using these exact same techniques? Keep exploring, keep optimizing, and we will see you in the next explainer.